Good morning, everyone, and happy Friday. Welcome to the Tejano Virtual Events Happy Math Hour, our weekly interactive math reviews for the Math 1314 and for Math 1324, which are presented by Yvette Chuca, Ruben Carizales, and Mr. Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come back and watch it. Thank you. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with information we will be sharing. We're going to be sending out the link for the 1324 room link on the chat so that you may connect to your session if you're here for the Math 1324. We'll also be sending individual messages to everyone to gather your students' ID numbers and to sign you in. And without further ado, I'll pass it on to our presenters so that they may begin.
Hello, everyone. Happy Friday. So today we're going to go ahead for Math 1314. We're going to go ahead and cover Exam 2 review problems. And if you're here for 1324, go ahead and click the link that they posted so it can take you to the other room. And so I guess we'll get started. First, I'm going to cover some examples from chapter section 2.6, since we haven't done any of those in our last happy hours. But this whole review will have questions from 2.1 through 2.6. At any time, if you have any questions, please let me know. You can either raise your hand, put it in the chat, whatever works for you. So for 2.6, we have some functions here. And these are called rational functions. And if you notice, most of these rational functions kind of look like a fraction. And so for this example, we're going to be looking at the domain, identifying the intercepts, finding the vertical and horizontal asymptotes, and then we're going to graph the rational function. So we look at the first part. To find a domain, we want to see, is there any numbers that will cause us to have a 0 in the denominator, since we cannot divide by 0. So to do that, we can either, one, we can ask ourselves what number will x be to give me a 0 down here? Or in other problems that are a little more complicated, what we can do is we can set the denominator equal to 0, and then we can solve for x. So if I subtract 3 on both sides, then I get x equals -3. So this number, we cannot use it in our function, because if we put -3 in our denominator, then we end up with a 0 and we can't divide by 0. So our domain is going to be everything except for -3. And so that's going to be the last option here. The next thing we want to do is find the x-intercept. So to find the x-intercept, we let y equal to 0 and we solve for x. So I'm going to go ahead and do that. In order to solve for x here, I'm going to multiply by x plus 3 on both sides. And so on the left side, 0 times x plus 3 is going to be 0. And 1 divided by x plus 3 times x plus 3 is going to give us 1. So if you notice here, 0 does not equal 1. That's a false statement. So what that means is that we have no x-intercept. So we would enter does not exist into the WebAssign homework. For the y-intercept, we're going to let x equal 0. So if x is 0 and I substitute 0 for every x and simplify, then we're going to end up with 0 plus 3 is 3. So we end up with 1/3. So my y-intercept will be 0 and 1/3. Now we want to find the asymptotes. So the vertical asymptote is basically can be represented with a dotted line. And what that means is that the graph will get close to that line, but it's not going to touch it. So to find the vertical asymptotes, we factor the numerator and denominator completely, and then we cancel any like terms. Then we set the denominator equal to 0 and solve for the variable. If you cancel any like terms in step 1, then it's going to create a hole in the graph. Okay, so let's start with step 1. So I cannot factor 1 anymore. It's already factored. X plus 3 is already factored. So now we just go to step 2. We set x plus 3 equal to 0. We're going to subtract 3 on both sides. And so x equals negative 3 is going to be our vertical asymptote. And so when you graph it, it would be this dotted line here. And then the horizontal asymptotes. So there's 3 options. If we look at the degree of the numerator and it's less than the degree of the denominator, then we say that y equals 0 is going to be your horizontal asymptote. But if the degrees are the same, then to find the horizontal asymptote, we're going to take the leading coefficient of the numerator divided by the leading coefficient of the denominator. And then the third situation is whenever the degree of the numerator is greater than the degree of the denominator, then what we would say there is that there exists no horizontal asymptote. However, if the degree of the numerator is 1 more than the degree of the denominator, then there exists a slant asymptote. And so we'll be able to look at these examples here in a few minutes. So here I have a number 1 in my numerator. So the degree of this term up here is going to be 0. And then the degree of my denominator here is going to be 1. So I have a 0 and a 1. So the degree of the numerator is less than the degree of the denominator. And so that's going to be option 1. So what that means is that we have a horizontal asymptote at y equals 0, which is really our x-axis, represented by this blue dotted line. Okay. So now let's put all our pieces together. So we had no x-intercept. We had our y-intercept, our vertical and horizontal asymptote. So to be able to graph this, we're going to plot additional points. So first I would graph the vertical asymptote. And then the horizontal asymptote is right here. So I'm going to go ahead and plot my y-intercept is 0 and 1/3. So that's represented here with the green dot. And then I want to pick some points. So you want to make sure to pick points on the right side and the left side of this vertical asymptote. So if I pick -2 and I plug it in to our equation, we get 1 divided by -2 plus 3, which is going to be 1. And if I use 2, just so I can be sure, maybe have a little bit more information here, I would get 1 divided by 2 plus 3, which is 5. So 1/5. And then I'm going to pick some on the left side of the vertical asymptote. So we plug in -4 for x. We're going to have -4 plus 3 is -1. So 1 divided by -1 is -1. And then if I choose the -5, we would have -5 plus 3 is -2. So we end up with a -0.5. So you can pick as many points as you need. I always like to pick at least a couple on both sides of the line. So if we plot these points, here are my points after I plotted them. And now we connect the points with our graph. And you can see here that our graph is going to get closer and closer to this vertical asymptote, but it's not going to pass it. And the same on the left side. Okay. So that would be our graph for the function f of x equals 1 divided by x plus 3. I think I have a couple more different situations. So here, it's the same type of problem, but the equation is 3x plus 2 divided by x plus 3. So let's break it up into pieces. State the domain of the function. So first, we take our denominator, set it equal to 0. And we're going to have x equals -3. Should not be part of our domain. So our domain is going to be all real numbers except for -3. So that's the second option here. And let's go on to step B, find the x-intercept. We're going to set y equal to 0, which is right here. And then we're going to multiply by x plus 3 on both sides. And when I do that, On the left side, I get 0. On this side, the x plus 3 will become 1, or they cancel out. So we get 0 is equal to 3x plus 2, subtract 2, and divide by 3. So my x-intercept is x equals negative 2/3. My y-intercept, we let x equals 0. So if I substitute 0 for x, then we're going to have 3 times 0 is 0 plus 2, and 0 plus 3 is 3. So my answer would be 2/3. And then now we're going to find the vertical asymptotes. So first, you want to ask yourself, can I factor the numerator? We cannot factor that any further, and I cannot factor the denominator any further. So this is ready to go. So to find the vertical asymptote, I'm going to set the denominator equal to 0. Subtract 3 on both sides, so we get x equals negative 3 is going to be our vertical asymptote. And so this is what it would look like. Horizontal asymptote, we want to look at the degree. So in the numerator, the degree is 1. In the denominator, our degree is 1. So the degree is 1 for the numerator, 1 for the denominator. So those degrees are equal. And so that's going to be option 2. That means that our horizontal asymptote can be found by looking at the leading coefficients. So y is equal to the leading coefficient of the numerator. So my leading coefficient here is 3. And then the leading coefficient of the denominator is 1. So we would have 3 divided by 1 is equal to 3. So that's going to be your horizontal asymptote. So again, if the degrees are the same, you're looking at the leading coefficients to help you find that asymptote. If we put everything together, I graph my asymptotes here. My x-intercept is negative 2/3 and 0, so right here. And then my y-intercept is 0 and 2/3. And so I need to figure out more information. So we're going to plot some more points. And you want to choose points that you feel will help you finish this graph off. So we're going to need some points on the left side over here, and maybe a few more on the right side so we can know how it's behaving. So if I use negative 2 and I plug it in for every x, we would have 3 times negative 2 plus 2 is going to give us negative 4. And negative 2 plus 3 will give us a 1. So that's going to be negative 4. I'm also going to plot a 2. 3 times 2 is 6, plus 2 is 8. And then 2 plus 3 is 5. And then on the left side, if we plug in negative 4, 3 times negative 4 is negative 12, plus 2 is negative 10. And negative 4 plus 3 is negative 1. If we divide, we get positive 10. And the same for 5, negative 5. 3 times negative 5 is negative 15, plus 2, negative 13. Negative 5 plus 3 is negative 2. Divide negative by negative will become positive. So if we plot these points, we have negative 2 and negative 4. So let's see, negative 2 and negative 4. That's this point here. Then we have 2 and 8/5, somewhere around here. And then we have negative 4 and 10, and negative 5 and 13/2. So we connect our points. We know that the graph should get closer and closer to the vertical asymptote and to the horizontal asymptote, but will not cross. Okay, so that was the second option when the degrees are the same. Now we'll go to the last option. So here we're going to look at h of x is equal to x squared minus 9 divided by x. So again, we look for the domain. So we set our denominator equal to 0. So here would be x equals 0. So our domain would be everything except for that number. And so that's the last option. Our x-intercept, we're going to set y equal to 0 and then solve for x. So I'm going to multiply by x on both sides. So on the left side, I get 0 times x is 0. On the right side, the x and the x will cancel. And so we end up with 0 equals x squared minus 9. I'm going to go ahead and add 9. So I end up with 9 equals x squared. To solve for x, we're going to take the square root of on both sides. So we get x equals plus or minus the square root of 9. The square root of 9 comes out to 3. So in this example, my x-intercepts are 3, 0 and negative 3, 0. If we get the y-intercept, we let x equal 0. So we're going to substitute a 0 in for all my x's. And so 0 squared is 0, minus 9 is 9. But then we can divide by 0. So what that means is we have no y-intercept. Okay. So now to find the vertical asymptote, this is what I mean by factor. X squared minus 9, we can factor it as x minus 3x plus 3. Our x is just going to be x. So here we cannot cancel any term because they're not the same. But if the denominator was x minus 3, then you could cancel out the x minus 3. In this case, we can't cancel anything. So we set the denominator equal to 0. And so that's going to tell us that the vertical asymptote is x equals 0. Horizontal asymptote, with the degree. The degree is 2 for the numerator, 1 for the denominator. So that means that the degree of the numerator is greater than the degree of the denominator. So when that happens, that means that there's no horizontal asymptote, but we need to check if there's a slant asymptote. To figure out if there's a slant asymptote, then we would look at whether the degree of the numerator is 1 more than the degree of the denominator, which in this case it is, since we have a 2 and a 1. So that tells us that we're going to have a slant asymptote. So how do we find this slant asymptote? We can use synthetic division, or you can use long division. So here I have x squared minus 9 divided by x. So remember that, let me take my pencil out here really quick. So remember that in order to use synthetic division, we're supposed to divide by c, right? Well, in this case, I only have x. So that means that my c is 0. So that's why I have the 0 here. Now for the other coefficients, if we look at x squared, the number in front of x squared is 1. So I would have a 1 here. There's no x, so it's 0. And then we have negative 9 for our constant. So we're going to bring down the 1. 0 times 1 is 0. 0 plus 0 is 0. 0 times 0 is 0. And negative 9 plus 0 is negative 9. So we get our quotient. So since I had x squared, we go with 1 less. So this would be x. It would be our quotient. There's no constant, and then this is our remainder. So once you get your quotient, that's going to be your slant asymptote. So the equation of the slant asymptote would just be y equals x. So how does that look? Let's put it all together. So my dotted line here is my y equals x, so that's my slant asymptote. Here are my two x-intercepts, and then my y-intercept is down here. And so I need to pick a few more points. And if you're not sure what the graph is going to look like, and so I'm going to go ahead and pick f of 2. So when I plug in f of 2, we get 2 squared minus 9 is going to be 4 minus 9 equals negative 5 halves divided by 2. Excuse me. And then 4, we do the same. So here we would get 16 minus 9 divided by 4 is 7/4. I'm going to try some on the left side over here. So negative 2 would give me 4 minus 9 is negative 5 halves. And then we get the 7/4. So if we plot these, then this is what it looks like after we plot them. So I can connect them together. And so my graph is going to just look something like this. Okay, so it's just going to get closer and closer to the line, but it's not going to touch it. So this was just a little 3 examples on 2.6. Now we're going to go back to some of the previous sections. So this problem here, write the quadratic function in standard form. Identify the vertex and the axis of symmetry. So this problem's from section 2.1. So in order to write the standard form, I always like to separate my x's here. So I have 2x squared plus 8x. Then we're gonna have to take half of b. B is the number in front. Well, before we do that, we need to make sure that your x squared, the coefficient is a 1. But notice here I have a 2. So first I'm gonna factor out the 2 so that I can make it a 1. So when I factor it out, I get a 2 and 8. If I factor a 2 from 8, I get a 4. So in other words, 2 times x squared is 2x squared. 2 times 4x is 8x. Now we're going to take half of 4. So half of 4 is 4 divided by 2 is 2. And then we're going to square it. So half of 4 is 2, and then 2 squared is going to be 4. So that number that we get, we're going to add and subtract into that parentheses. But then we want to get rid of this negative 4 from the parentheses. So we're going to pull it out. But if I pull it out, I have to worry about whatever's in front of the parentheses. And so we're going to multiply those together. So when I take out negative 4, I have a 2. So negative 4 times 2 will give me a negative 8. The reason we take it out is so that whatever's left in here is going to be a perfect square. Why can I do that? We're not changing the problem because 4 minus 4 is just 0. So we're just adding 0. However, we are making it look a little bit different. So now what you want to do is factor what's left in the parentheses. So x squared plus 4x plus 4 is going to be x plus 2 times x plus 2. And we can rewrite it as x plus 2 squared. And so this is my equation in standard form. And from this equation, I can take the vertex. The vertex is represented by the number in the parentheses. So if you have a plus 2, we use a negative 2. And then the outside constant is negative 1. So that's going to be your vertex. The axis of symmetry is always going to be the x coordinate of the vertex. In this case, x equals negative 2. So if you feel like you need more help on standard form, we do have a whole session on this in one of our other Friday Happy Math Hours. And so in a little bit, they'll be posting up the YouTube page. You can go find the videos there for previous sessions. But the next big thing in chapter 2 is to find the real zeros and determine the multiplicity of each zero. So here I have f of x. It should be f of t. So f of t is equal to t to the fourth minus t cubed minus 30t squared. Since you want to find the zeros, your first step is to set it equal to 0. So here I'm going to set it equal to 0. And then you want to ask yourself, do my 3 terms have anything in common? And if so, we want to factor that out. So they all have a t squared in common. So I'm going to write t squared out here. So t to the fourth, if you factor out a t squared, you're going to be left with t squared. T cubed, if you factor out a t squared, you'll be left with 1t. And then negative 30t squared, if you factor out the t squared, you're left with the 30. Now we can look at the parentheses. Can that be factored? It can. So negative 6 times 5 is negative 30. But if I add negative 6 plus 5, I get a negative 1. Now that I have all factors, I can set each factor equal to 0 and solve for t. So here we would take the square root on both sides. So we would end up with 0 is equal to t. Here I would add a 6, so I get t equals to 6. And here we subtract 5, so we get negative 5 equals to t. Notice that the degree is 4, so you should have 4 zeros, but we only see 3. Okay. The other 0 comes from the t squared. Here we're producing 2 zeros, so another 0 would be t equals 0. Why is it 2 zeros? One, the t squared, you can write it as t times t, and then you can set t equals 0, t equals 0. So that is where your other one comes. So this 0 is repeated twice, and twice is an even multiplicity. So that means that the graph is going to touch and then turn at that 0. T equals 6 only appears one time, and t equals negative 5 only appears one time. So at the graph, at this 0 is only going to cross. So they both have multiplicity of 1. It didn't ask to graph it, but if you were to graph it here, you can see these are my zeros, and at my 0 for this one here, the graph crosses. At 0, it touches and turns, and then over here, it's going to cross as well. Then we talked about end behavior. And so in order to do the end behavior, you have to look at the leading coefficient and the degree. And so I always tell my students, you can memorize the definition, which is kind of long, or you can try to think of graphs that you're familiar with. So by now, hopefully when you see f of x equals x squared, you know what the graph for that looks like. And then we have negative x squared. You know, this is the one that opens down. And then we have x cubed, so that's going to look like this one. And then negative x cubed. If you know these 4 graphs, then you will be able to figure out the end behavior. So if we look at x squared, that has an even power and a positive leading coefficient. So the behavior, it rises to the left and it rises to the right. If it has a negative coefficient, then it's going to fall to the left and fall to the right. If the coefficient is odd with a positive leading coefficient, if the degree is odd with a positive leading coefficient, then we say that the graph rises to the right and falls to the left. And if it's a negative, we say that it rises to the left and falls to the right. So for example, if we have 12x cubed plus 6x, the degree for this is 3. So that already tells you that your behavior should be like the 3rd graph or the 4th graph. So we look at the number in front of it, it's 12, that's positive. So that means that your behavior should be like the x cubed behavior. So we would write as our answer that the graph rises to the right and falls to the left. So that's how we would use the end behavior. The multiplicity, again, if you use these graphs that are familiar to you, then we can see at x squared that the graph touches and turns. And so the reason is if you solve x squared equals 0, you're going to get x equals 0, x equals 0. So it's going to have an even multiplicity. At x cubed, this is going to come here. It's going to cross at that point, and it has an odd multiplicity. That means that it repeats x equals 0, x equals 0, x equals 0. Okay, so if you forget the rules, think about the graphs that you're familiar with to help you. So now we'll jump into possible rational zero theorem tests. This is from section 2.5. And the reason we want to use this is because this is going to help us find the zeros, but it creates a smaller list than the infinite amount of zeros that we have, or possible zeros. So to do this, we're going to look at the factors of the constant term, which is this one, and the factors of the leading coefficient, which is this one here in red. And so the way it works is if I have this polynomial and I want to find the rational zeros, I can use this test. So I'm going to find the factors of 9, which are 1, 3, and 9. So the factors are just the numbers that you can multiply together to give you that number. So 1 times 9 would be 9, and 3 times 3 would be 9. The factors of my leading coefficient is 1. So the factors for that is just 1 times 1. And then we're going to write them in this way, in this ratio here. And so here we would have our constant terms are 1, 3, and 9. My leading coefficient is 1. So if we divide, 1 divided by 1 is 1, 3 divided by 1 is 3, and 9 divided by 1 is 9. But we're also including the plus or minus. So on the computer, you don't have a symbol for plus and minus. So you would have to enter your answer as negatives and then the positives. So why is this important? Well, from this list here, instead of checking an infinite amount of numbers, I can choose one of these numbers to see if it's a 0. So I always like to start with 1. So let's check 1. So then I use synthetic division. So here I have a 1. X squared leading coefficient is a 1. My x leading coefficient is negative 9. My constant is -9. So if I bring down the 1, 1 times 1 is 1, 1 plus 1 is 2. And then -9 plus 2 is -7. So I'm going to know that if this is a 0, if our remainder is equal to 0, so 1 times -7 is -7 plus -9 gives me -16. So that's not a 0. So this means that 1 is no good. Okay, so it's okay. We try another one. So how about -1? So I bring down the 1. 1 times -1 is -1 plus 1 is 0 times -1 is 0 plus -9 is -9 times 1 is +9. Oops, I went too fast. Well, so now you can see it's a 0, so that's going to make us happy. Why? Because 1, it tells us that x equals -1 is a 0. And now we can take our quotient. So since we had x cubed, we're going to start with x squared. So this one will be x squared. There's no x. And then my constant is -9. But the reason we had that big happy smiley face is because now that we know this was a 0, we got our quotient, and notice that our quotient is now quadratic. So we have options to solve this. We can use the quadratic formula, we can factor, you can use the square root property. So any of the methods that you feel comfortable with, I'm going to go ahead and use the square root property. So I'm going to add 9 on both sides, and I'm going to take the square root on both sides. So I get x is equal to plus or minus 3. My degree is 3, so I should have 3 zeros. And my 3 zeros are -3 and 3. And of course, the -1 that we got from the synthetic division. Okay, so if you're giving a problem like this on your exam, find the zeros, then this would, well, one, there you can try to factor this by grouping. And if it factors by, then you can definitely use that method, but not all, they don't all factor by grouping. So if they don't factor by grouping, then your next choice would be to use the possible rational zero theorem, so that you can make a small list of numbers that you can check, like I did here, and hopefully one of them is going to be able to give you that remainder of 0. Okay, let's go on to the next one. Just the factors here, if they give you a 0, then the factor, if we bring the -1 to the left side, that's going to be your factor, x plus 1. In this case, bring the -3 to the left side, we get x plus 3. And then we bring the 3 to this side, we'll get x minus 3. So here's one where we're going to put it all together and graph it. So my degree is 4. That means I should have 4 zeros. So we're going to find the possible zeros. Then we're going to get the real zeros. Then we're going to graph it. So notice here that I don't have a constant, right? So let me go a step back. Let me get my pen really quick. So if you're using the rational zero test, remember we're going to use P over Q. So the factors of my constant, well, there's no constant, right? Your constant is 0. So my factors are just going to be plus or minus 0. And then your leading coefficient is 1. So that's plus or minus 1. Well, 0 divided by 1 is just 0. So there's no, your list, you don't have a big list. You only have one number to check. So let's go ahead and do that on the next slide. So here's 0. So I'm going to have a 1 for my x to the 4th, a -1 for x cubed, a -6 for x squared, 0 for x, and 0 for my constant. So I'm going to bring 1 down. 0 times 1 is 0, plus -1 is -1, times 0 is 0, times plus -6 is -6, times 0 is 0, and then 0 plus 0 is 0, times 0 is 0. So the good news is that this 0 is a 0. And I know that sounds crazy because we know it's a 0. But I'm referring to it's a 0 on your graph in your x-axis, right? It's an x-intercept. So the other good news is, okay, since that works, we can get our quotient. So let's get our quotient. Since I had a power of 4, my first power here would be 3. So I'm going to have x cubed negative x squared minus 6x. So now the problem here is that this is cubic. So they all have an x in common. So you can try to factor out an x. And that would probably save you some time, because you would end up with x squared minus x minus 6. Actually, let me just write that here. Let me get my pen. So even from the very beginning, the first you want to try is to ask yourself, like even at the very beginning here, do you have anything in common that you can factor out? And if you can, then that could save you a lot of time. So in the beginning, we could have factored out an x squared from each term. But I wanted to show you the process of using synthetic division. Sometimes some people want to just stick to one method, and that's okay as well. But like here, before we repeat this, if you factor out an x, then you get x squared, then you get a minus x and a minus 6. And then we're going to have, you can factor the inside now, right? So you're going to have x times x. Negative 6 is 3 times 2. I want the x to be negative, so the bigger number would be negative. And then we add it. So now here I can say that x is equal to 0, x minus 3 is equal to 0, and x plus 2 is equal to 0. So my zeros would be 0. This one would be a 3, negative 2, and then my other 0 is repeated. Okay, so that is one way that you can go, is if you are able to factor, if you're comfortable factoring. But if you're not, it's okay, because this method will work okay. So if we repeat the process, then there's no constant, so I'm going to use 0 again. So my 1 comes from 1, my negative x squared is negative 1, a negative 6, and then my constant 0. So if I use synthetic division, notice I end up with 0. So I can get my quotient now. Since I had a cube, I'm going to start with x squared. So we get x squared minus x minus 6. Now it's quadratic, so now you have options. You can use the square root property if you want. Well, in this case, you can't, but you can try to factor. You can use a quadratic formula. So as you notice in the page before, I did factor this. This is factorable, but I'm going to use the quadratic formula just to show you a different option. And so if you use the quadratic formula, you plug in all your information, then you notice that you get x equals 3 and x equals negative 2. So your zeros are 0, 0, negative 2, and 3. The multiplicity of 3 is 1, so it's going to cross. Negative 2 has multiplicity of 1, so it's going to cross. And then 0 appears twice, so it has an even multiplicity. So it's going to touch and turn at that graph. Determine the maximum number of turning points. To find the turning points, we use n minus 1, where n represents the degree. So we say the degree minus 1. So we have degree of 4 minus 1. So this should have 3 turning points at maximum. So when you're graphing, the first thing I encourage you to do is plot your zeros. So remember, my zeros were negative 2, 0, and 3. Next, you want to apply the end behavior. Okay, so let me go back here. So this is even. So my end behavior, what is it going to be? So let me just draw this really quick. So is it going to be, let's call this A, B, C, or D? So what do you think it's going to be? If you want, put it in the chat. A, B, or C, how is this going to behave? To get your answer, you look at the degree and you look at the leading coefficient. Okay, so any ideas on how this is going to behave? A, B, C, or D? Okay, so your degree is 4, that's even, right? So this has an even degree, this has an even degree. And then, so that means our answer would be A or B. Since you have a positive, that means that we're going to have letter behavior. Okay, so let's go to the next page. So at the last zeros that you see, you want to apply that behavior. So I know this is going to go on in this x equals 3. I know that my graph is going to cross, so I kind of have my graph crossing, and I know it's going to rise to the right. And at x equals -2, I know it's going to cross, and it's going to rise to the left. So now I need all the in-between. So to get all the in-between, we're going to plot some points. So you want to plot points on the left side and right side. So if you have -1 and you plug it in for all your x's, then you're going to end up with -4. If you plot in x equals 1 for all your x's, you're going to end up with -6, which is right here. And then if you plug in a 2 for all your x's, we're going to end up with -16 down here. And so if we plot this, connect our points, then the graph will look something like this. So this is just a sketch. The real computer graph, this is what that looks like. Okay, so me as an instructor, I'm looking for different things. I'm looking, does the student know what the end behavior was? Do they know what to do at each zero? As far as do they know that they have to cross or touch? And did they plot a few extra points to complete the graph? And so if your graph has all those requirements, it looks similar to what the graph should be, then you would get the credit from me. Okay, so now we're almost, I think I have like 2 or 3 more examples, but this one here says find the polynomial function with the given degrees and the solution points. So our degree is 4, so that means we should have 4 zeros. And I only see 3, okay? So the 4th zero is going to be the conjugate of, I only see 3, okay? So the 4th zero is going to be the conjugate of that imaginary 0. So you want to get the factors. So the factors of x equals -4 is x plus 4, and then we have x minus 1, x minus I, and x plus I. So we're going to set it up as a polynomial, and I'm going to use an as my leading coefficient because I don't know what it is. And I encourage you to multiply the imaginary parts first. Okay, so we get x times x is x squared, x times I is ix, negative I times x is negative ix, and -1 times 1 is I squared. The ix and the negative ix will cancel, so leaving us with x squared minus I squared. You could totally use the shortcut if you know it for multiplying conjugates. If not, you can just do what I did here. I squared, we know that's equal to -1, right? So let's simplify negative, negative. That's going to be positive. And so this is what I have now. So now I just have 3. So now let's multiply 2 more together. So x times x squared is x cubed. X times 1 is x. -1 times x squared is negative x squared. -1 times 1 is -1. Gather like terms if you have any. I don't see any. So now we're going to multiply times the next factor. So x times x cubed is x to the 4th. X times x is x squared. X times negative x squared is negative x cubed. X times -1 is negative x. 4 times x cubed is 4x cubed. 4 times x is 4x. 4 times negative x squared is negative 4x squared. And 4 times -1 is -4. And gather our like terms. So we have x to the 4th. We have negative x cubed and a positive 4x cubed. So that's positive 3x cubed. Then we have an x squared here, a negative 4x squared. So that's a negative 3x squared. Then I have an x, negative x, and positive 4x is positive 3x minus 4. So as you can see, now we have a polynomial here. Now we just need to know what that leading coefficient is. So we're going to use the solution point. F of 0 is telling me here that x is 0. And when I enter x is 0 for all my x's, then I should end up with a negative 8. So what I can do is my function here, my y value is negative a. Anywhere I see an x, I'm going to replace it with the 0. So all of these terms would be 0. So I'm going to be left with negative 4. Divide by negative 4. So I get a 2. So my leading coefficient is 2. So to finish the problem up, we're going to multiply everything by 2. So 2 times x to the 4th is 2x to the 4th. 2 times 3 is 6x cubed, and so on. And so this is going to be our polynomial function. And if you work it backwards to find the zeros, then you should end up with these zeros here. All right, I believe I have one more, and it's an exciting one, right? So for this last one, it says use the given 0 to find all the zeros. And then they give you the function, and then they tell you that 4 plus 2i is a 0. So what we can do is, since it gives me that 4 plus 2i is a 0, what I can do there is take this information and I can use synthetic division. So that's one option. We also know that 4 plus 2i, there's another 0, right? Which is the conjugate, 4 minus 2i. So you can multiply those together. And then, well, we'll stick with this one for now. But so let's take 4 plus 2i here. And then I have a 1 minus 12, 52, negative 80. So we're going to bring the 1 down. And then I'm going to multiply 1 times 4 plus 2i. And so now we get negative 12 plus 4 is negative 8 plus 2i. And then we're going to multiply 4 plus 2i times negative 8 plus 2i. And so if we do that, we have 4 times negative 8 is negative 32. 4 times 2i is 8i. 2i times negative 8 is negative 16i. And 2i times 2i is positive 4i squared. So let's simplify this. So 8i minus 16i is negative 8i. Negative I squared, or I squared is negative 1. So that's a negative 4 plus a negative 32. And so if we put them all together, then we end up with negative 36 minus 8i. So you might be thinking, well, it's kind of looks a little bit worse, right? But it's going to get better in a little bit. So once we simplify this part, we still have to add it to the 52 plus negative 36 is 16 minus 8i. And then we do the same thing all over again. 4 times 16, 64. 4 times negative 8i, negative 32i. 2i times 16, positive 32i. 2i times negative 8i is negative 16i squared. So notice here, negative 32i plus 32i, that cancels. I squared is negative 1 times negative 16 is plus positive, and I'm just showing you the work there. So positive 80 plus a negative 80 is 0. So if you don't get 0 here, then you know that you did something wrong because they tell me it's a 0, so my remainder should be a 0. So you might be thinking, well, it doesn't look like it did anything, right? But one, since this was a cubic, we can start with quadratic now. So this one is x squared. Negative 8 plus 2i, that's going to be your x, the leading coefficient of your x. And then your constant is 16 minus 8i. So we're going to go ahead and we can repeat the process. But this time I'm going to use 4 minus 2i because my conjugate, instead of 4 plus 2i, I also know that 4 minus 2i is a 0 because it's the conjugate. And then I'm going to use this. So x squared has a 1. The x has a negative 8 plus 2i, and then we have 16 minus 8i. So I'm going to bring the 1 down. 1 times 4 minus 2i is 4 minus 2i. So negative 8 plus 4 is negative 4. Positive 2i minus 2i cancels. And so we multiply again. 4 times negative 4 is negative 16. Negative 2i times negative 4 is positive 8i. So the imaginary parts cancel. 16 minus 16 is 0. And so now, since I had x squared, I'm going to start with x. So 1 would be x, and then I have negative 4. So the good thing is to finish this, we can set that equal to 0 to find our last 0. So what are our zeros? X equals 0. No, that's wrong. So the 0 should be x equals 4. And then our two imaginary numbers, x plus 4i and x minus 4i. This should be a 4. And that was it. And so the only other part we didn't get into as much is the complex numbers. We did a little bit of them there, but if you have any questions, let us know. I want to wish you all the best. Some of you are taking exam 2 starting next week, okay? And so also you can always download this presentation by, if you notice up here where my mouse is, there's a box with an arrow pointing down. You can click on it and save it. And then I encourage you to look at our recorded sessions as well. But thank you guys.
Thank you, Mrs. Ivetshuka, for your wonderful presentation. If you'd like to download a copy of the presentation, you can go up to the top right corner and click on the box with the arrow going down while the presentation is on the screen. We want to remind you all about our previously recorded sessions, which are available on the YouTube playlist. This session will also be available on that playlist later today. Also, link is a short survey to help us improve our TV sessions. Please take a few minutes to fill out that survey. Before you leave, I want to share the TV sessions that we'll have next. There's a flyer here, and we're gonna have at 1 p.m. today. We have degree plans. And we will be back with the Happy Matter next week at 11 a.m., where Math 1314 will cover exponential and logarithmic functions, and Math 1324 will cover basic matrix operations and inverses. Our 1 p.m. sessions next week will be getting involved in EPCC clubs. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or your mic, and we hope to see everyone again for Happy Math Hour.